So this is a crocheted bit of the hyperbolic plane, also known as the non-Euclidean plane, because it is extremely non-Euclidean. Euclidean geometry will be the geometry that you'll remember from school. For example, at some point you might have learned that given a line and a point not on that line, there's exactly one parallel through the point to the line that you started with. And what this is showing is that in the non-Euclidean plane, it's just not true. So here we have 3 green lines, all of them going through the same point, and none of which intersect the black line. So these kinds of models are really helpful for understanding non-Euclidean geometry. They were developed by Dinah Taimina, and lots of mathematicians make them to make diagrams like this, because what's nice about this piece of crochet is if you want to figure out what the lines are, if you had, say, a piece of an ordinary plane, like this piece of paper, if you want to know what a straight line is, you can just fold and crease it, and the crease is naturally going to lie on a straight line. And it turns out the same is true of this. So in order to make these diagrams, I found the lines by folding this over until it lies against itself, and then the creases that you get are straight lines. But the reason why I'm talking about this in this section about growth is because of the way that you make this surface. So this is constant negative curvature, and the way that you achieve that is you increase the number of stitches that you crochet in each row, and you do it so that the number of stitches grows exponentially. So each time, the number of stitches in the next row is the same factor times the number of stitches in the previous row, and it gives you this shape. It also gives you some really weird patterns in the crocheting, though, because the increases in the next row are a little out of sync with the increases in the previous row, so you get these weird syncopated effects. And in order to see what that looked like, I made this piece, which is hyperbolic constellation. And so this is bead crochet, so every stitch has a bead on it. Every 7th stitch is in gold. And so every time I hit a gold stitch, I would increase. So this shows exactly where the increases happen that give you this negative curvature. And you can see that the arrangement of gold beads is kind of funky. Like sometimes they line up, sometimes they spread out. So it's a fun little experiment. So the piece right here has a simpler version of this type of growth. This is knit bifurcation, and here the stitches double at regular intervals as you go outward from the center. So in the center, there's 1 column of stitches, and then there are 2, 4, 8, and 16. So it's the beginning of this sequence that shows exponential growth when you take the powers of 2. The work next to it at the end of the line has a slightly more complicated growth structure, and so it grows like the sequence on the bottom here, which might look familiar. This is the sequence that you get when you start with 1 and 1, and then for each number you add the previous 2 numbers to get the next one. So this continues 2, 3, 5, 8, 13, and so forth, to give you the Fibonacci numbers. Probably how you've heard it described. Actually, the Fibonacci numbers were described about half a millennium before Fibonacci by Vera Hanke. And so for that reason, this piece of knitting is called Vera Hanke's Thoughts Overflow. And the branching of the columns of stitches follows a simple recursive rule, the result of which is that the number of columns grows exactly like the Fibonacci sequence. Now, if you look at the Fibonacci numbers, this is not exponential growth, but it turns out the further out you go in the list of Fibonacci numbers, the closer it is to exponential growth, the closer you are to having a fixed factor from each number to the next. And so that's the reason why you get that same negatively curved flared shape.